Let us start today from a simple experiment that Joule did about 170 years ago and which paved the way for a real revolution in thermodynamics. The first evidence that other quantities further to pressure, specific volume and temperature exist comes from a series of experimental observations carried out by Joule between 1843 and 1848. The most popular among these experiments is the one in which he raised the temperature of a quantity of water almost completely surrounded by a perfectly insulated, in other words adiabatic, wall by means of a stirrer which was operated by a falling weight. The result of this experiment was an exact proportionality between the amount of work expended on the water and the rise of its temperature. The result is 4.184 kilojoules are needed to raise the temperature of 1 kilogram of water for 1 degree centigrade. In each one of the experiments, water was enclosed by an adiabatic wall, a perfect insulation, and showed an external source of work that, when set into motion, created a change of state of the fluid within the enclosure. Surprisingly enough, the same proportionality was obtained from all these very different methods of transforming work into temperature rise. Let us focus on the stirrer experiment. Here, the potential energy of the weight is that part of the energy of a body which is due to its position. Further to finding a proportionality constant between heat and work, an additional and maybe more important essential result from the Joule's experiment is that it now allows an application of the concept of potential energy to the field of thermal phenomena involving changes of temperature and pressures. We state the existence of a quantity, characteristic of the fluid, such that the loss of potential energy of the wave is transferred to the fluid in form of an increase of energy of the fluid. In addition, we can state that the energy exchanged is independent of the path taken to move between the two states and may thus be written as a difference. Therefore, this energy internal to the fluid depends only on the initial and final states. For this purpose, we construct a new function u, we call it internal energy, which depends only on the internal state of a body, as determined by its temperature, pressure, volume, and composition. Pressure, temperature, volume, and composition are the macroscopic manifestation of intermolecular forces internal to the fluid. Therefore, internal energy could be theoretically assessed also from electrostatic calculation on the interaction among the molecules in the fluid. This is not the attempt of engineering thermodynamics. Engineering thermodynamics has proudly a macroscopic approach that describes mathematically the link between changes of internal energy due to changes in pressure, temperature, specific volume, mass and composition. In absence of any other energy change, such as kinetic or potential, for example, the total energy of an adiabatic thermodynamic system is the internal energy. Therefore, we can write this dependence of u from its independent variables as u function of temperature, volume, and mass of each one of the species in the fluid, which determines the composition. The same expression can be written in terms of moles. Since P, volume, and temperature are correlated in a homogeneous system, two independent variables among them would suffice. So we could use temperature and volume, as in the case written here, or temperature and pressure, for example. The two ways would not make any difference as long as we have an equational state to move from one set of variables to another. You have now learned how, through a series of experiments, Joule proved the existence of one fixed quantity of energy needed to increase the temperature of 1 kilogram of water of 1 Kelvin, and that this quantity is the proportionality constant between the potential energy of a body moving vertically and the increase of temperature of water. From these two evidences, we can postulate the existence of an internal potential of the fluid called the internal energy that depends on the intermolecular forces in the fluid, which show macroscopically as a state at a certain temperature, pressure, volume, and composition.